Greetings, salutations, all those nice things. Today we are beginning topic 8. A trig identity is a trig equation or statement that is always true for all permissible values of the variable used. And there are a bunch that we might know already, but we'll be using these to manipulate, simplify, compare trig expressions. We'll show that certain expressions are equal to other ones, and we'll look at some complex identities. But first, we need to talk about the three reciprocal identities. Now, we have looked at sine, cosine, and tangent. There are, secondary trig functions as well. So while sine, cos, and tangent are our primary trigonometric functions, we can also talk about these three called cosecant, secant, and cotangent. And they're defined as follows. Cosecant is the reciprocal of sine, secant is the reciprocal of cosine, cotangent is the reciprocal of tan. Because they are the reciprocals, these are called the reciprocal identities. And if we want, we can write these a different way. We don't have to. But if cosecant is the reciprocal of sine, then we can say that sine is the reciprocal of cosecant. And similarly, if secant is the reciprocal of cosine, we can say that cosine is the reciprocal of the secant function. And finally, if cotangent is the reciprocal of tan, we can say that the tan function is the reciprocal of the cotangent function. It's not necessarily necessary to memorize any particular way, but we should absolutely know the definitions of these three right here. There are also quotient identities. Quotient is the result of dividing, as we know, and they're based on the relationship between sine, cosine, and tangent. So we did actually directly reference this in the most recent lesson in 7.4, but you might have seen this in the earlier years too, the fact that tan of x is equal to sine of x over cosine of x. And there's a number of ways you can get that. If we look at right triangles, where that's totally a right triangle, and we've got our opposite and our adjacent and our hypotenuse, if you take sine of theta, which is opposite over hypotenuse, and divide it by cosine of theta, which is adjacent over hypotenuse, then by simplifying this complex fraction, we just get opposite over adjacent, and that's the definition of tan x. Now, of course, that is just based on right triangle trigonometry, but that right triangle trigonometry does give us a basis for our understanding of every other bit of trigonometry. And since cotangent is the reciprocal function of tan of x, we can also give this the old flippy-do and say that cotangent is the reciprocal of this, which means it's the flipped over version of that. We can, if we want, also represent tan x and cotangent of x in terms of secant and cosecant. So looking at tan being sine x over cos x, we can say that sine is related to cosecant. We can say that cosine is related to secant, and use those definitions to get a different way of expressing tan x. So looking at that one, we have that, I don't know how to spell. Tan of x is equal to sine of x divided by cosine of x. And thus we can say that tan x is the result of taking 1 over cosecant of x, since sine is the reciprocal of cosecant, and dividing it by 1 over secant of x, since cosine is the reciprocal of secant. in simplifying this, we're dividing by a fraction. So we can just rewrite this a little bit. We have 1 over cosecant x being multiplied by secant of x over 1. And then to finish simplifying this, we can say that tan of x is secant of x over cosecant of x. So now we've got tan represented in terms of secondary trig functions instead of the primaries. Take a moment, see if you can get cotangent of x also represented without just saying, well, we got to flip this over. Or prove it the same way. I will. So cotangent is the result of taking cosine and dividing it by sine, and that's from our quotient right here. And then replacing cosine and sine with their definitions in secondary form, we can say that we've got 1 over secant x divided by 1 over cosecant x. And changing that to a multiplication statement instead, we've got, oopsie daisies. Yeah, that is what I wanted. That. And thus we can say that cotangent of x is cosecant of x divided by secant of x. Note that the variable's there the whole time, so we're never saying that cotangent is equal to cos divided by sine. Like, we might use that in a more colloquial sense, just to say that, well, the variable's presence is understood, but in a written form, that variable does have to be there the whole time. So we can't just say cotangent is cos over sine. That is incorrect. If you put that on a paper, I do have to actually mark it as incorrect in that it's missing a variable in a function. So do not do that. As anticipated, what we got on this side is just the flipped over version of that, because tan and cotangent are reciprocals of one another. But there it is. There are the identities. Again, you don't have to memorize all of these. The ones that you should be memorizing, I just want to get rid of these extra lines. Nailed it. The ones that you should absolutely be remembering are these ones up here. So the definitions of the secondary trig functions. And these ones. So these definitions of tan based on the primaries and cotangent based on the primaries as well. Because we have these identities, these other ways of expressing trig expressions, we can simplify particular trig expressions that use these. So we could simplify something that looks like this. It looks a little gnarly. Let's see what happens if we manipulate things a bit. There's a number of ways to play with this. What would I do? I have a tendency to want to express things in terms of how you say the primary functions. But if you don't, that's up to you. You just need some way to re-express cotangent and some way to re-express cosecant or some way to re-express cosine. We have options at our disposal. One thing that I might do is express cotangent as a ratio between cosine and sine. So my numerator is now that. And I might consider expressing cosecant as 1 over sine x. So the only changes I've made there are to express cotangent as cos over sine because of that quotient identity, and to express cosecant as 1 over sine based on the definition of cosecant based on that reciprocal identity. To simplify this further, we have to note that we're dealing with a complex fraction, and we need to take care of that. And there's a bunch of ways we can do so. I'm going to simplify the bottom just a little bit, rather than have two separate factors. make it 1. So I'm just going to lower this a bit, actually. Sorry. Just going to make that a bit bigger. Hey, now. That'll work. All right. So on top, I've got cos x over sine x. On the bottom, I've got, well, 1 over sine x times cos x means I have cos x over sine x. And now I've got something divided by that same thing. So this is actually equal to 1. What a world! This super interesting expression is actually just equal to straight up 1. Didn't see that coming. That's just life's little mysteries. Math's little mysteries? And there it is. Of course, there are cases where that wouldn't be true, and that's just because this expression right here has some non-permissible values. So it's good practice to always be aware of those non-permissible values. You don't necessarily have to always be considering them in terms of what final answers could be or when it comes to identities, but just noting that the non-permissible values exist and that these identities only maintain their truth value if those non-permissible values aren't encountered. 1 has no non-permissible values, but this thing does. And in finding that, I'm thinking to myself, what makes us divide by 0? There's a number of ways we can get non-permissible values. Division by 0 is one of those. Taking the square root of a negative, having a negative argument for a log. There's a variety of ways we can get non-permissible values. And with these reciprocal identities, or with sine and cosine, we're essentially looking at dividing by 0. Where can that happen? We divide by 0 right here if sine of x is equal to 0. So whenever sine of x is equal to 0, we're dividing by 0. If cosine of x is equal to 0, then we are also dividing by 0 because this whole denominator would be 0. So we're also dividing by 0 in that case. And finally, we've got wherever cosecant of x is equal to 0. So if cosecant of x is equal to 0, then we're dividing by 0. All right, where did these things happen? Bloop. We know how to solve this one. I mean, you can look at the graph of y equals sine x if you want, but sine x is equal to 0 at multiples of pi, essentially. So we could say 0 plus 2k pi and pi plus 2k pi, or just to make that a bit more succinct and condense it, it's just any multiple of pi. So the sine of any multiple of pi will be 0. Similarly, cosine of x has zeros somewhere. Whoop. There's how it goes. Where does that happen? Cosine of x has zeros whenever we have x be pi over 2, or 3 pi over 2, or 5 pi over 2, or 7 pi over 2. So noting that, we're looking at pi over 2 plus any amount of whole entire pi's. Oops, I'm missing things. But hopefully that's something we're kind of already aware of. Where is cosecant of x equal to 0? Whoa. Well, sine of x looks like this. I switched colors, that's magical. Cosecant is the reciprocal of that. So how are we going to get 1 divided by one of these values is equal to 0? Spoiler, we can't. And that's kind of because of the fact that cosecant is 1 over sine of x. If you want that value to be 0, the only way for a fraction to be 0 is if its numerator is 0. Its numerator is not 0. Its numerator is 1. So this thing will actually never be 0. It's so sad. If you want to see another reason for that happening, if you want to see that happen graphically, sorry, I have to make a new graph here. Then functions-wise, looking at cosecant of x gives us that. Now we can have this step go in pies instead. So this is the graph of y equals cosecant x. It looks like that. And it's never equal to 0. It's so sad. Any poopsilies, we're going to try a few more. Well, actually, no, we should finish this one off, sorry. So what are non-permissible values here? These ones right here. And we could say that that's the set of all, you'll see, k pi from here, and all the pi over 2 plus k pi's from here, such that k is an integer. Or if we actually want to make that more succinct, which we can, it's actually just every single multiple of pi over 2. Oops. If you see that. That's all. Anyhow, see if you can write each one of these in terms of just a single trig function. So 3 examples. I don't know where to go with these. I do, but give them a try. Just explore around a bit, because a lot of these solving identities that we'll be doing eventually is going to involve what I might call just stumbling for a bit, like getting a sense of what we can do and where it goes. So try them, try rewriting them, and then I'll jump in as well. I will jump in now. Hopefully you have tried this. Please make sure you have tried it before seeing this go down. I'm going to write cosecant as 1 over sine x. And I'm going to rewrite tan of x as sine of x over cosine of x. If I simplify this, I just have 1 over cosine of x. And this is in terms of a single trig function. But if we want to just make it not have a fraction involved, I can say that 1 over cos x is equal to the secant of x. And that one's done. So either one of those works. This next one, I don't really feel like rewriting sine or cos, so I'll keep those same. But tan, I'll rewrite as sine x over cos x. It's such a great one. Gotta love tan. And the cos x's will cancel each other out, so I've just got sine x times sine x. And to write that a bit more succinctly, it's sine squared of x. And this final example, whoa! All right, we've got a bunch to rewrite here. I'm going to rewrite this whole thing first without changing anything. I'm just going to change this. Oops, I forgot my variable. So I'm going to write it that way. And then I'm going to convert that. So I've got secant of x, which is 1 over cosine of x. And I'm dividing that by sine x times cotangent of x is cos over sine, since tan is sine over cos. So I'm dividing by this whole thing. Which means I'm taking this 1 over cos x and dividing it actually just by cosine of x, which is fun. So if we want to rewrite that for multiplication purposes, we can say we're multiplying by the reciprocal, which means we've got 1 over cos squared of x, and so this works. Or if we want to phrase that without any fractions involved, we can say that that is the square of secant of x. And that works too. Whew, what a doozy. I strongly recommend practicing this. We're really going to want to get a feel for what identities we can use in any given situation, and what options there are, and which ones we should go with. And getting that sense is just extremely necessary for moving ahead. So do make sure you do that practice work that's listed there. And of course, let me know if you have any questions whatsoever. Again, the more questions you ask, the more I can answer. And the more we can all move forward together. That's it, that's all. You have yourselves a most lovely day. And I will see you in the future. Bye.